Hello, I'm here to present the paper Experimental Analysis of a Modular Solar Chimney. The authors are Cristiana, Brasil, Maia, me, and Janaína, Castro, Silva. The work was developed at PUC Minas. I will start with a brief description of the operational principles of a solar chimney. A part of the solar radiation incident on the cover passes through the cover and hits the ground, increasing its temperature. The ground hits the air, which rises due to buoyancy forces, leaving the device through the tower. A turbine is usually placed at the bottom of the tower. As the main advantages of the device, we can say a few. It uses both direct and diffuse components of solar radiation, managed to operate even when there is no instance of the direct solar radiation. It can also operate at night using the heat stored at the deeper layers of the ground. It uses simple technology and widely available materials. It has low maintenance cost, simple operation, and high durability. However, it presents some limitations, since large structures are required to be built. The installation costs are high. It has low efficiency of conversion of solar energy into electricity. For this reason, solar chimneys are currently being used, combining, for instance, power generation and water desalination. The result of the low efficiency is that large areas are required to generate power at competitive prices. Although large plants are required to generate power, small-scale plants can use the hot airflow generated for applications such as thermal comfort and agricultural drying. Most of the studies in literature concern large-scale plants, and only a few describe small-scale plants. Of these, we didn't find any study regarding modular plants or any study describing plants in Brazil, except the ones of our group. So, the objectives of the paper are to design and build a small-scale modular prototype of a solar chimney in Belo Horizonte, and to evaluate the influence of the main geometric parameters on the airflow. The prototype built is modular, as you can see in the figure, and we can change the main geometric parameters. The tower is made of PVC to ensure a light and resistant structure. The collector here is horizontal, made with polygons of thermodiffuser film, normally used in greenhouses. The system was placed on a blackened surface, and it was applied a concrete layer over the ground to avoid the migration of humidity from the ground to the airflow. It was defined a standard geometry with a tower height of 2.5 meters, a collector diameter of 5 meters, and a collector height of 0.1 meter. And we changed the main geometric parameters and height tower 1, 1.5 to 2.5, collector diameter 3, 4, and 5 meters, and collector height 0.10, 0.15, and 0.20 meters. The airflow parameters measured were the temperature. We measured ambient temperature and the outlet airflow temperature. The relative humidity, we measured it at the inlet and outlet of the system to evaluate the migration of humidity from the ground to the airflow, and the solar radiation outside the device. The mass flow rate was estimated using this equation adapted from the literature. Well, The influence of the geometric parameters was evaluated by comparison of the results for each parameter varied to those obtained with the standard geometry. The results are presented for a 24-hour test and on an hourly basis. We evaluated the ambient parameters like solar radiation and ambient temperature, and the airflow parameters, outlet airflow temperature and mass flow rate. The first parameter evaluated was the collector diameter. We evaluated 3, 4, and 5 meters, which corresponds to the standard geometry. This first graph represents solar radiation versus time. We can see that the values of solar radiation for the test of the standard geometry were lower than the others. The ambient temperature follows the same behavior of solar radiation with lower values. We can see that the average ambient temperature for the standard geometry was 24 degrees Celsius, while the other ones were close to 28 degrees Celsius. The first graph represents the outlet temperature. It can be seen that lower values are obtained for the standard geometry, attributed mainly to the lower levels of solar radiation. When the other are compared, 3 and 4 meters, it can be seen a slight increase of the outlet temperature with the collector diameter. Increasing the collector diameter, the heated area increases, increasing the airflow temperature. The mass flow rate also increases with the collector diameter, since the driving force of the airflow increases. The second parameter was the tower diameter, evaluating 0.10, 0.15, and 0.20 meters. It can be seen that for the lower dimension, 0.10, the solar radiation was higher, resulting in higher ambient temperatures. An increase in the tower diameter decreases the outlet temperature and the mass flow rate due to the increase in the heat transfer area, allowing to lose more heat to the environment, increasing the heat losses. And the last parameter is the tower height, 2.5 meter for the standard geometry and 1 and 1.5. The solar radiation and ambient temperature did not present so large variations as the other parameters. We can see that an increase in the tower height increases the pressure difference between the top and the bottom of the device, increasing the driving force of the airflow and the mass flow rate. The outlet temperature decreases with the tower height. The results follow the literature for the general behavior of the airflow. Since studies of similar dimensions were not found in literature, particular values could not be compared. But the main conclusions are: the mass flow rate is more affected by the tower diameter and tower height. An increase in the tower dimensions in general increases the mass flow rate. The outlet airflow temperature is more affected by collector diameter, since it has a more effect on the heat absorbed. And when the collector diameter is increased, it's possible to heat a greater portion of air, increasing the airflow temperature. We would like to thank PUC Minas, FAPEMIG, CAPES, and CNPq. If you have any further questions or want to discuss anything, feel free to email me. Thank you.